Okay. Thank you for coming. I know we were up against the Perl 6 JVM, which is kind of a very hot topic. I'd like to be there myself, so thank you for coming. Perl Memory Use. Perl uses lots of memory. Who's encountered this problem? Okay. And if you're on Linux, maybe this one? Or maybe this one? It's not a way to become popular. But generally, things just slow down. You know, swap space starts getting used, and it's paging, and just, things get painful. So, a quick tour of process memory. Do you have a pen and paper? Because we're going to spend 20 minutes looking at these numbers. Does anyone know what units those numbers are in? There's a slightly better way. I won't torture you that much. Stad-M. Does anyone know what units those are? PS. PS makes it a little better. But still, what units are those? But top's good. Top actually tells you the units and it behaves sensibly. So we're going to be looking a lot at virtual size. But before we do, I want to kind of take a slight detour into the resident size. Or at least kind of dig down deeper into the structure of memory. This is the nicest way to see what your process is doing, looking at the proc status, if you're lucky enough to be on Linux. So VM size, that's the size of the whole thing. If you're interested in how much memory your process is using, that's the one to look at. Or possibly VM data, which is kind of the variable bit that all your Perl stuff goes in. The RSS is the resident set size, which is just how much happens to be in physical memory at the moment. And these are your segments. You've probably heard of a segmentation violation. Well, these are the segments that get violated. So you have a little bit of C code at the top, and then read-only data, read-write data, your heap that grows, and then a bunch of shared libraries, and then your C stack. That isn't your Perl stack, that's the C stack growing that way. And the way you can see these on Linux very clearly is through the maps, proc maps. And there you're getting one line for every segment. And you can see the permissions, read, write, execute. And that's your segmentation violation. If you try to write to something a segment that you don't have write permission on, you get a segmentation violation. Okay, now for each one of those lines represents a segment. If you look at the SMaps file, then for every single segment, you get this block of data showing you how big the segment is, how many pages are mapped, and all sorts of other stuff that I don't even pretend to know what I'm talking about. So from the process's point of view, it has big chunks of continuous memory in these segments, especially the heap. You know, a lot of work goes on in the heap. But the operating system's view is very different. The operating system thinks in terms of 4K pages, or usually 4K. And it's continually trying to juggle the physical 4K pages amongst all the processes that have memory. So here's a very bad diagram trying to show that 4K pages of physical memory are kind of being mapped in and out of all the processes that are trying to use them. So the reason I kind of stress this point is quite a lot of the modules on CPAN that try to tell you how much memory you're using are actually measuring the resident set size, which is just wrong, because even while a process is growing, the resident set size could be going down if some other process is accessing a whole bunch of new memory pages. Yeah, then the kernel's going to be giving the physical pages to that process. Your process is still growing, but the resident size is going down. Okay. So, malloc and the heap. I think it'd be a great name for a jazz band. Okay, so the heap, that's where we need to pay attention. That's where all your Perl stuff goes. But between Perl and the heap is malloc. And malloc sits there, and Perl asks malloc for little chunks of memory, and Perl sometimes gives them back to malloc. But malloc very rarely gives them back to the operating system. It's kind of a one-way street. If you ask for a big data structure, kind of 16K maybe, then malloc will give you that as a memory mapped chunk, as a chunk of memory, mapped memory, that when you free, it'll free that back off. But it's very rare that the ordinary sort of malloc use gets free back. So let's have a look at some Perl internals. When you write your Perl code, you think in terms of integers and strings and arrays and numbers and all that kind of thing. But inside the Perl internals, there's lots of tiny little data structures. So here are three of them: integer, string, and a number with a string. And at the bottom there, you can see head, body, data. All scalars have a head. Sorry, all values in Perl have a head. Most of them have a body and some of them have data. So an integer is optimized now just to be a head. So that's 4 words, you might say. That'd be 4 32-bit chunks on a 32-bit machine or 4 64-bit chunks. Strings also have a body and then a variable size length. The bodies are all fixed size depending on the type. And then a number with a string has a body and the data. Arrays, slightly more complex. You have the head, the body, and a variable sized head, body, variable sized data with all the pointers to the elements in the array. Now hash starts getting very fiddly. Lots of little bits and pieces for the bucket chains, hash entries and hash keys and the iterators. And then we get into globs. I'm not expecting you to learn this stuff. The point I'm trying to make here is that there's lots of tiny bits of memory strung together with pointers. I hope you'll agree that it's kind of gets sort of crazy when you're trying to debug this stuff, as a few of us have lived to tell the tale. So what tools do we have to look inside all this stuff, all this data? Well, develop peek is a handy one for looking a little way in. So you can give it a reference to something and it'll show you a couple of levels and give you some of the internal information. So there you can see a reference to a hash, and down at the bottom you see the element in the hash, and you see the 12 bytes is the current length of the string and 16 is how much was actually allocated. Now that makes the point that there's how much data you think is being used, how much is actually being allocated from malloc, and then malloc behind the scenes will have its own overheads associated with its buckets and fragments and whatever. And in the Perl internals, if we go back to here, the heads and the bodies now are all allocated from arenas, which is kind of very efficient fixed-sized allocation scheme, but still there's overheads. And one of the interesting side effects of the arenas is that there's an arena for each type of body. So if you allocate 1,000,000 arrays and then you free them again, in the arenas that hold the bodies for the arrays have 1,000,000 bodies in that will never be freed. Now they're there for you if you want to create another 1,000,000 arrays. But there's kind of there's a disconnect between how much memory your Perl process actually is currently using and how much the operating system has to give it, because there's these 2 layers of buffers. There's the malloc doing its own sort of buffering, fragmentation and admin, and then you've got these arenas doing the same thing. Okay, arenas. Devel Gladiator can kind of show you how much is in the arenas. And Devel size. Now we're going to be talking a bit about Devel size. Devel size doesn't give you an insight into the structure of what's there. It just sums it up. It has the logic to chase all the pointers. Created in 2002 by Dan Sugalski, Nick Clark has done great work maintaining it and keeping it up to date with all his changes to the internals. Nick's done amazing work with optimizing the internals on the Perl 5 porters list with a whole bunch of good people. So this is great. This has the logic, but it just gives you a number. It just says I have this much. So I've already mentioned all that, What you want to know is what you can do about this. That's what I want to know, because when I did MIT Prof, people say, well, could you do the same thing for memory? So, so the original thought was maybe we could kind of measure memory usage going up and down the same way we do for CPU usage. And Nick Clark again did some great experiments with that, but it just turned out not to be useful. You know, you kind of know where memory gets allocated most of the time, and you know where it gets free. What you really want to know is what's holding the memory. And actually that can lead to some interesting surprises. So lexical variable, out 10 meg, call the function, return 20 meg still being used. Why is that? Does anyone know? Well, first, sorry?
It's the $var for future use by calls to foo has been saving space.
That explains 1 10 meg.
Oh.
So 1 10 meg is because the buffer for the $var lexical is being preserved, ready to take the next value the next time you call the subroutine.
Is it saved the constant?
Yes, constant folding. The compiler very handily said, oh, X is constant and the 10 meg is a constant. Let's build you a 10 meg constant string. And I'm just going to keep it here to one side. So when you call the function, I can just copy it into the value you want. That's where your 20 meg is. But we've never had a way to see this. Here's another example of the same thing, 10 meg string, but this time we recurse. Now we recurse 50 times and now there's a gigabyte. What's going on there? Well, every recursion level has its own pad. So what we saw happen before with the preservation of the buffer of $var, that happens at every level of recursion. So if you have recursive subs that have a lot of throwing strings around a lot, it gets very expensive. But we have no way of seeing it. What we need is a way to look inside the box, take off, lift the hood, sort of poke about, see what's going on. So the only sensible way, dawned on me last year, was that we just have to call the whole thing, call all the pointers. And devel size has the logic. So what I need to do is to extend it with a callback hook so I could kind of hitch a lift as it crawls around the pointers. I needed some way of naming where I was as I crawled around the tree. Dump the stuff to disk, store it, process it, manipulate it, visualize it, that kind of stuff. All very experimental. Would you like to see it? Okay, live demo. What could go wrong? Okay, now I'm actually going to do lots of little live demos, and this used to drive me nuts, so I wrote a script to do the live demos for me. So it's not quite as dangerous. So devel size me, the interface is a bit funky at the moment. If you don't set the size me environment variable, it acts just like devel size, mostly. So I set that devel size me variable, and I say, give me the total size of this integer. So there is your IV, and there's the address of the IV, and there's a 24-byte head. Now let's try string.
Can you increase the size, please?
Oh, increase the size, yes. Hey, okay. So we have a 24-byte head, 16-byte body, 13-byte svlen totaling 53. Now we'll do a random number, and then you have the head and an 8-byte body. Now we're going to do a random number that we're going to stringify. We're going to use the number in a string. And now we have the head, 24, but the body has been upgraded. It's been upgraded from an NV to a PNV, so it's gone up from 8 bytes to 32 bytes. And there we have the length of the cached string representation. Arrays. Okay, now we're getting somewhere. So we have an array, and there's the head and the body and the buffer for all the pointers. 3 elements, an integer and a string and a number. And then a few notes. It kind of annotates this information as its output. And there's various other bits and pieces. There's sequence numbers and depths and things like that. Okay, now that text is coming out of devel size itself. If you pipe the output to a program, then it writes out the same information but as tokens. So that lets you write another program, devel size me store, that will read the tokens and manipulate the data as it passes through. So this looks very much like the one you saw before, but this has gone through some tree processing. You can't actually see what it's done, but it's there because you can then write different data outputs. Now, this information, it gets really old looking at pages of this. You can't really sort of see how big the substructures are. What you need to do is visualize. Ka-ching. So there's your array with your 3 elements, so your integer and your number and your size. And you see the size is there and then totaled up. That's sweet. Now, let's try it with an array of 2 hashes. So there's an array, 2 references, 2 hashes with 1 element each, integer, integer, and here you can see that the hash key is shared. Okay, now so this was seen twice. One of them has a solid line, one of them has a dash line, and the dash line says, well, this is an alternative route to something that I've seen before. The software needs to get smarter about picking which of the alternative routes gives the best name, and that's kind of something I haven't got into yet. So another thing that we can do now is Devel size has very hard to understand logic about what pointers to follow. Devel size me is now driven by ref counting. So effectively you're answering the question, how much memory would be freed up if I destroyed this thing I'm passing to you? So because we're checking all the references, we can see when we get to something that we don't get all the references to. We don't see all the references. So here is a reference to an array that we haven't completely seen. So we don't own it. So we're going to identify it here and show the ref count, but not actually traverse into it. Now, let's have some fun. Haha, subroutine. What does a subroutine look like? Well, there you are. That's what a Perl subroutine looks like. So you have a CV. This is the CV outside for those who know the internals. There's the ops. I'll talk about that in a sec. Pad list. So there's the names of the pad, and there's the myx. And then here's your pad. And bum, 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 bum. So you can see, even in that little factorial function, my shift x, return, a few variables, one line of code, one line of very simple code. Your pad has a whole bunch of bits and pieces in there. And then up here, that's the glob. Okay, now you see this, even this one line piece of code has 3 cop files. Now the cop files are used to record the name of the source file. So if your source file is down some long path, each one of those will be a long path. Now this Perl I'm using is a threaded Perl, and I filed a bug report recently to say, hey, threaded Perl is using vast amounts of memory to record the name of the file for every single statement in the file. We're talking hundreds of kilobytes. So hopefully that'll be fixed in 520. And that was shown up by being able to visualize this stuff. So let's now it's the same function, but I'm going to call it. So the only difference here is I'm calling this recursive function. And now it's off the charts. So here you can see your 3 pads. Whoa, I've killed it. Right. Okay. I know we're getting complicated here. There'll be smoke coming out soon. Okay. So here you can see your pad 1, pad 2, pad 3. And again, they're being totaled up. So now this function only has 1 variable. But every level of pad is using like 200-300 bytes. And you can see here it all gets a bit complicated with all these pointers, but because some of the values are shared. Oh, what's going on there? It's all going to end in tears. Okay. So how about we look at a whole package? This is not working. Sometimes the graph is on this, gets a bit upset. Actually, I could do, ka-ching, okay, and start that again, get back to where I was. Right, exporter. So this is the whole of the exporter. Now you can see here there's like a lot of detail, and it's getting a bit crazy. So these hash, the hex and the he's that kind of make up the components of the hash, they're not terribly interesting. Okay, I just won't touch the keyboard. How about that? And also there's all there's cop files around somewhere. Where have they gone? Oh no, I think I've hidden those now. Yes, nope, they're here, cop files. So there's a lot of detail, so it's getting hard to see the bits you're interested in. So I added a mechanism, oops, haha, that's not going to work now. I added a mechanism, here we go, just to hide bits that you weren't interested in. So now, cross your fingers. Yay! So now this is the same thing. I'm just trying to build attention. This is the same thing, but without some of the detail. But still, it's kind of getting hard. That's going to get old, isn't it? On wiggle wires. Okay. It's still, you can see it's kind of getting hard to visualize. If you imagine a big program, it gets... Help! Right. I'll just describe the diagrams, okay? So now that was exporter. How about we try main? Now this is very likely to kill Graphis. So how big do you think main's going to be? Well, it's so big that you have to do that. And there is main. Now this is a program that does nothing. This is just, you know, there's nothing here. So it was kind of very pretty and useful when it's small. It's kind of impressive and useful. But at this stage, it's just impressive, but it ceases to be useful, which isn't good. I don't like, you know, impressive is good, but useful is better. So what we've been doing so far is totaling the size of a data structure, but you can also size the whole Perl interpreter. Apply that logic to absolutely everything, and there's a lot of stuff that you kind of might not think of. When you think of a Perl interpreter, you think of your stuff, you think of your packages and your variables, but there's an awful lot going on behind the scenes. So I'm not even going to try to render that, because it would just be crazy. So that's half a meg spread over 5,000 nodes. And you know, once you get to about 2,000 nodes, then Graphis just kind of gets very sad. So what we do now, rather than writing a dot file, we'll write a database, a SQL-like database, and rather than doing a Perl size, you can go one level higher up, and there's a heap size function that also includes the information from malloc, if you have a malloc that can tell you that information. So what do you do with the database? Well, what you do with the database is you visualize it with a tree map. So I have this little web server, and it's visualizing your tree of information that you've seen as a tree map. And here you can see 10 meg in your heap, most of which is malloc, and then you Perl interpreter here, and inside the malloc you can drill down and you can see, well, there's 5 meg of free space sitting inside malloc. And this 3 megabytes is the difference between everything that I've sized up here and what malloc says has been allocated. So that's 3 meg that I haven't accounted for yet, so I'm going to keep working to reduce that. But let's have a look inside the Perl interpreter, because that's much more interesting. So Perl interpreter, main, others, freed. Main is kind of where that's def stash. That's where all your package stuff is. That's your main stash. Others I'll get back to in a sec. So here's your main. The B library, oh yeah, this I was loading moo. So that you might have seen in the example down here, this was loading moo, just for the sake of loading something. Does that fit? Oh look, we can make that a bit bigger. Can you read that at the back? No. Okay, well, too bad. You'll have to come forward, but just be grateful it's on screen at all. Okay. So there's B and dynoloader and base and constant, and obviously the size of the box is how much memory is being used. And then over here is just a bunch of internal stuff I'm dumping there for the sake of making it visible. And you can drill down. So you can click on one of these, B section, output, and basically it boils down to just clicking on the biggest box. And you click on the biggest box and go, oh, why is that using so much memory? So here you can see this is a CV, and you see a path up here with kind of the nodes and the links between them. Ops. So you can see there's 5 kilobytes of ops in the output function of the B stash. Yeah. Oh, pad list. Let's look at a pad list. So you just kind of wander around, you know, it's like going for a walk and seeing where all the memory is being used. Now, if we're lucky, yeah, that was the demo I hope would get working, but it's not going to. That was a production machine that I'd done a size me of some XML processing. Okay, let's nip back up to the Perl interpreter and peek into the others. Any questions so far? And how much time do I have? How much time is left? 17 minutes. Excellent. Okay. So, others. Now, devel size me works by following the references. So, when you ask for the Perl size, it starts def stash and does all that and everything else it can find, but it will stop whenever it comes to something that has a ref count greater than the number of times it's seen it, then it just sort of bumps up the number of times it's seen it and goes off and looks elsewhere. So if you have a reference loop, at the moment it waits until it's looking through the arenas, the kind of the structures that have all the SVs, and it says, okay, is there anything that I saw but didn't see enough? And it says, okay, that must be a ref loop, so I'll go and break the ref loop. In future, what I need to do is kind of rework this so that at that point, the data that comes out should be reparented to the appropriate place in the tree. So at the moment, it's kind of off to one side in this ref loops. And I'm not going to click on this, because if I do, it'll just die in pain. Because if you have something that has lots and lots of structures, and that's just a few, but sometimes you can have tens of thousands, then the browser gets upset. Doesn't like dealing with tens of thousands of divs. This is your string table. Whenever you have a hash key in Perl that's shared, you may remember that from an earlier slide, they're shared in something called the string table. So this is the string table. It's all the stuff that we didn't account for elsewhere. Sub-exporter progressive. Not sure why that's there. But anyway, this is kind of a dumping ground for stuff that I haven't sorted out better homes for yet. Any questions?
Were there used to be colors on this before?
Colors. You'll see colors shortly, but I haven't got round to actually colorizing this in nice ways. But there's another visualization I'll show you shortly.
Flame graph has colors.
Oh, Flame Graph has colors. Yeah, you're in the wrong presentation. That was last year. Yeah, Flame Graph is so old now. So this will be nicely colored and polished up. My JavaScript and HTML skills are not great. Okay, any other questions? Will this be useful? Yes. Awesome. Okay. So the tree map it's very scalable. Yeah, you can throw a lot of data at it and just drill down. Works very nicely. But it's a very narrow perspective. You're just at one point in the tree, looking at what's below you in the tree. Excuse me. What I've always wanted to be able to do as soon as I got into this was to visualize the whole tree in like the way you can do with graphics, but on a grander scale. So one of the other things this store can do is write a JEXF file. So I'll get it to do that. And it writes that out. And then Ching starts Gephi, or Jeffy, depending on what side of the pond you're on. And now, okay, I'm going to import that file. And there is your Perl interpreter. Isn't it pretty? Okay, let's make it a little bigger. Okay, slightly prettier. And now let's do something more interesting. Let's partition by the type. Ooh, now is it pretty? Colors, okay. Now let's do some ranking by the size, and we'll choose a rank parameter of the size. Now is it pretty? Okay. Now let's scale that up. Actually, there's no point scaling it up because what I'm going to do now is I'm going to do a layout. I like this bit. This is my favorite bit of the demo. This is every point here is a data structure, and every line is a pointer. And the data is the data from a Perl interpreter that has just loaded moo, nothing else, not a big job. And what that was doing is laying out the network, trying to lay it out in a way that allows you to see structure and clusters. Now, we have the coloring, But really, it's kind of, this is one of those things that's still much more on the impressive side than the useful side. But let's see if we can make it a little more useful.
Is the large ball B?
Oh yes, yeah, I should explain what these things are. Let's find out what they are. So that is, what is that? Bytes 3, yeah, that's the bytes 3. So that's the space sitting inside malloc that Perl used to do the compiling, but then freed it back.
So the size of every node is the amount of...
Yeah, it's the size of the data structure. Now, most of the data structures are just tiny, you know, so small that I can barely click on them. Okay, there you go. Yeah? Okay, but this one, what's that one? What is that? Name, label, SV, len, trim. I have no idea what that is.
B? I'm guessing B.
That's the
ones
height
that
of
against me.
big.
I don't think it's letting me click on that. I don't know why it's confused. So let's see if we can scale to node size. Give me labels. Now, is that going to work? So this is kind of where I'm at the moment. Whoop. There's a label, bytes 3. I'm going to shout that at you. Now these things, I think, remember these being, yeah, these are, what are they? What are you? So what I need, clearly, this is kind of great fun to play with, but I need to tip the balance now between impressive and useful, because there's a lot of information here. Also, I suspect there's just too much information, so this one in the middle here is, I think, the string table. So it's like, you know, every key of every hash and every data structure in the entire interpreter kind of hangs off that. So, you know, it's not terribly useful. So what I need to do is work on filtering so that you can actually see the wood for the trees. And the coloring's nice, and I can polish that up. So, but it's kind of hard to see. Also, the kind of the size of the dots should probably be logarithmic rather than linear, and things like that. So there's a lot of polish to do, and I've been feverishly working to get it to this stage for today. But there's a lot more. So if you're interested in helping out with this, because like I say, my JavaScript and HTML skills are very weak, so if you want to help out on the tree map side, that would be awesome. If you're familiar with Gephi, then it'd be awesome to have some help there with the data visualization. But clearly there's a lot of potential here to actually see what the issues are. So coming back to that XML parsing problem, we had some big job that was taking, say, a gigabyte of space, and there were lots of them running, and it was using up the memory. And it turned out that the problem was parsing a big XML document, you know, one that had started out small years ago, but was now very big. And it was parsing it, creating a data structure, and then freeing the data structure. But of course, you ended up with massive amounts of free heads and bodies that weren't being reused. So we're just going to change it to a streaming parser. And that's the kind of insight that we haven't been able to see before. And it was very obvious that there was a lot of information sitting in the freed heads. Let me go back to the tree map. Perl interpreter. One of the other things you can do, yeah, freed. Okay, so you've allocated a lot of stuff, you've freed it. As far as you're concerned, the memory is free. But actually, in here, these are the freed bodies. These are the size of the arenas. Now, there should be a count here, but the count's not working at the moment, to tell you how many freed bodies there are sitting there. One of these is probably, yeah, there's the SV heads. So if you create lots of variables and then you free them again, you'd find lots of free heads here, plus lots of whatever kind of body they were. Okay. Any questions?
So can I do this on any time during a live process, say db single equals 1, and then generate this, and then later on?
Yep. So at the moment, devel size me, you can call the function like you've seen me doing. And there's a hook set up, so you can say Perl-D: size me, and it will automatically call size me at the end time. Okay, much like MIT Prof does. So that's great. That's kind of a very simple way of doing it. You can also call the size me functions in multiple places, and each time it'll write out the file. You can use the environment variable to change where it's going. The data stream has a begin and end token in it, so my intention is that you'll be able to stream multiple runs. That visualization software actually supports streaming network changes, so it ought to be possible to have this dynamically updated by your calling the heap of a running process. You can say snapshot, 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 and this would update. Now, there's huge technical hurdles in getting that to happen, but it is possible. So that would be kind of awesome demo. That would be way up there on the impressive scale. I'm not sure how useful it would be, but it would just be awesome. So yes, I think that's answered your question. The token stream, the way it works, I was actually very pleased with the way that worked out. It's very efficient. Although it's chasing a bazillion pointers and writing out a lot of information, it's all done on the stack, and there's no malloc or free during the process. So it's blindingly fast. The only limit is how fast it can stream out the tokens. So if you pipe it to gzip, for example, then it's very quick. Now, processing the tokens afterwards gets a lot slower, but I haven't optimized that. I just need to run a profiler, maybe, to optimize it. I haven't yet. Any other questions?
So what's really the next step in terms of cleaning up your application after that? You've identified what stuff is free, but it's not truly free at that point.
So what to do with the data? Some data that's been freed is just one of the things that Devel Size Me is showing you that we've never seen before. So it's an easy one for me to look at because all I've done in that program was load moo. And so the freed space shows up a lot because that's all the work the compiler did, and then the compiler finished. So there was a lot of kind of workspace for the compiler that's been freed, but I haven't got the program to do something. So if you had a program that had been doing something, there would be a lot of data stashed in the program and in the pads and the references and the data structures. So you would drill down through the tree map following the big boxes to see where the memory is. Does that answer your question?
Yes and no.
Give me another question then. Give me another question.
Well, the compiler may take up 10 meg of memory. Right?
Yep.
But your application, once you're using it, is only going to be using up, and it's freed that, quote unquote, freed that. But your application's now only using a meg of that over. How do you free up that additional 9 meg, or can you? If your application is only using a megabyte, then you're a very fortunate person. So the Perl compiler here loading moo has freed up 10 meg that it was using while compiling. 10 meg is peanuts. Yeah. So as soon as you do real work in an application big enough to want to run Devel Size Me, you're talking hundreds of megabytes, and the freed space is a minor issue. I mention it simply because it's an issue that I ran into in production recently, where we didn't know where the memory space was, why so much memory was being used, and the answer was it wasn't being used, it had been freed. But it had been freed back into the Perl arenas and malloc, so the process was still very big, and Perl wasn't using it, so it was just an example that I was quoting. In most cases, you have reference leaks, for example, and so that would be data very much still in the Perl interpreter.
Perl version requirements?
Perl version requirements, it's actually Perl 5.8 up at the moment. The internals are hairy, to put it mildly, and it breaks encapsulation in so many ways.
It's really quite embarrassing, but there's no choice, because it just has to be down in the guts of Perl, and it has to do things in different ways for the different versions of Perl. But it does work on all versions of Perl 5.5.8 up. There are some things that you can't see until more recent versions, like the arenas, for example. I forget what version of Perl the arenas arrived in. It's probably 5.10. So there are minor differences that way, but basically it works on all modern versions of Perl, which I'm quite pleased about, really, and slightly surprised. There was another question?
If you take multiple snapshots, do you have any tools to visualize how your memory changed over time?
Not yet. So it would be very common. A classic case would be a web server, and you want to take a snapshot and fire some requests in, take another snapshot, and then visualize the difference. And the answer is not at the moment, but I'd love you to contribute one. It's an interesting challenge. It's not. It's an interesting challenge even within a single process run, because a lot of the structures should stay where they were at the last run, but your scalars, the scalar might have been freed and then reused, and it's being used for something else. So there's an interesting problem of trying to traverse two trees and work out what's actually changed. So that's a good challenge, but an interesting one.
How do we contribute?
How do you contribute? So the code is on GitHub, and there's a bug tracker, there's a mailing list, and there's an IRC channel. I've got it all set up for you. It's on CPAN right now. So I've been busy making releases and letting CPAN testers tell me all the portability problems. So it's on CPAN, and the details are in there. The documentation is minimal, and it's mostly up to date. So that's what I'm going to be doing after the talk now, is just checking the documentation, make sure it's all reasonably sane, and pushing another release. But it's on GitHub. So I hope to see you all on the IRC channel, and send me lots of patches. Tell me where it's broken, and tell me where it works too. It's always nice to have success stories. Any other questions?
In that early example you had with the scalar that's 10 megs, if you undef that scalar, does it give up the memory?
Okay, let's go back here to that one. No, not that one. Yes, that one. Okay. If you undef the scalar, now that's an interesting question. There's a subtle difference between, there's 10 meg in $var, and there's 10 meg in the temporary variable that the compiler created so helpfully for you. You can't touch that 10 meg that the compiler created. Sadly, this is a good reason for a use less pragma to say, hey, if it's crazy big, please free it off for me. The $var, if you've got an application that's slinging large strings around rather than references to large strings, if it's actually slinging large strings around, then yes, it's a good idea to undef the values. So a good case here is HTTP GET. So you're using LWP, you're downloading a big file. LWP in a couple of places will hold a string with the entire contents, and that buffer will always be the size of the largest thing you've downloaded. Yeah, so that would be an example of somewhere where it might be a good idea to do an undef. But if you did undef it, then every time you call it, it's got to reallocate the memory. So there's a trade-off. Yeah. So it's like it would be nice with the use less memory pragma to be able to say, please free buffers bigger than X amount. So if you do allocate something very big, then it'll get freed again.
If you can get rid of the 10 megabytes on the compiler by putting the exponents 10 million inside a string eval.
Yeah, okay, so you could get rid of the 10 meg by putting it inside a string eval. So it's trading memory for performance, CPU time versus memory. But yes, that's a good way to get rid of that. I mean, not many people have this specific problem. Obviously, I'm exaggerating here to make a point. Okay, any more questions? All right, thank you very much. Thank you.
All right, looks to be about 2:30, so I think we're supposed to start. So, okay, everybody hear me?